One of the most important attributes that a programmer must have is the capacity of separating complex patterns into smaller and more fundamental units of information. Identifying the basic unit of information in our programs will ultimately shape our capacity to implement those algorithms. We are going to start with a very simple library called Turtle. We are using the Python programming language because of its simplicity as an interpreted language. Keep in mind that building applications and implementing algorithms is something that transcends a particular programming language. You don't need to be a Python expert to create good programs. As a matter of fact, you don't need to be a programmer at all. To create programs, you can start with the algorithms. An algorithm is a series of steps that, if followed properly, guarantee the same result every single time. Of course, if the process is deterministic. If you bake, you have built programs. In our tutorials, we will divide our program in 3 different sections, called the modules, the data definitions, and the code. The module section contains the libraries, the programs that other people have written so that we don't have to. The one we will use today is called the Turtle. There is, in Python, 2 different ways to import libraries. The first one is by simply typing the command import followed by the name of the library. However, in this tutorial we will use a second way of importing libraries that starts with the command from. From has the ability of bringing a very specific module from inside of that library and put it inside of our project without the necessity of importing everything else. So I'm gonna import every single variable and module inside of that library by using the asterisk, which is a wildcard meaning everything. This is something that you shouldn't do in other circumstances. Because the Turtle library is rather small, there is a small chance that I have named my variables the same thing that the programmers that build turtles named theirs. Turtles are very simple machines. They understand 4 basic commands divided in 2 categories: movement and rotation. If I want the turtle to move forward, I can specify the name of the action followed by the number of steps that I want the turtle to move forward. The done command allows me to make the turtle wait while I perform the operations so that the program doesn't close. You can see here that a turtle that looks more like an arrow starts its journey at the center of the canvas and moves east 100 steps. The opposite of forward is back, which allows the turtle to move from its current location, tail first, towards the opposite direction where its head is pointing at. Besides movement, we can also modify rotation. We can make the turtle go right a certain number of degrees, and the turtle will rotate its head. The opposite of right is left. If we were presented with the problem of building a square, where would we start? The idea of building any shape at all requires an understanding on how much the length of each of the sides of the shape are and how much we need to rotate when changing sides. So let's start in the data definitions. We need 3 definitions of data. The first one will be the size. I start the name Didi because regardless of what this is for the Python language, this has to mean something for the programmer that goes beyond the scope of what the programming language itself can provide. This is the information of what the definition of this data represents so that I can build the algorithm. The next element is called the type comment. The type comment represents the data type and the name of the variables that belong to this type of information named size. In this case, it will be represented with a float primitive data type. This represents the size of each of the sides of a shape. The size will start at a value of 100. The next data definition will be the number of sides. Sides is an integer. It doesn't really make sense to talk about float values or decimal values when it comes to the number of sides that a shape has. The information's domain, the set of values that it can take, is restricted to integer values. This represents the number of sides that the shape will have. Sides will start at 4. And the last data definition we're going to build is called the angle. The angle will be also a float, and it represents the rotation between vertices that allow the shape to close when completing all rotations. The angle will start at 90. In school, they teach us that a square has a straight angle of rotation of 90 degrees. But where does this number come from? Let's take a look at different values. When the number of sides is 4, we have 90 degrees. When the number of sides is 5, we have 72 degrees. 64, 6, and so on. When the number of sides is 3, we have a number of rotation of 120. When it is 2, is 180. So what would be the value when the number is 1? We have a shape with only one side. How much rotation do we need? Let's put a question mark here. There seems to be a trend, a negative relationship between the number of sides of a shape and the number of angles we rotate. The bigger the number of sides, the smaller the angles. What happens if we multiply these values against each other? It turns out that all of them give the same output, which is 360. Which means that if we want a shape with one side, we need to multiply it by something that gives 360, and that has to be itself. So it seems that there is an important correlation between the number of degrees in a circumference and the number of sides that our shape is going to have. If we apply some simple algebra, we'll come up with the formula 360 divided by 4 to calculate the 90 degrees that lead to a square. But in our program, the number 4 represents something very special, something that we have called using variables. That is the domain of the data definition sides. The value 360 remains a constant. So I take this element and I paste it here. And now every time I change the number of sides, the angles of rotation should automatically be calculated. Let's move to the coding section and let's draw our square. The process of drawing the square represents the algorithm. So we need to identify what the basic unit of information is. It is a line. We make the turtle move forward. And then we make the turtle turn right. If we run this process, we'll see that the turtle moves forward and turns. It's just a matter of repetition. We take this basic unit of information and we paste it 4 times. But repeating the same snippet of code every single time for as many sides our shape is going to have is something that can quickly become quite tedious and hard to visualize even in the coding editor. That's what for loops are for. Loops in programming languages are tools that allow us to repeat the code for as many times as necessary. Sometimes we know ahead of time how many times we want to repeat a code, for which we use for loops. Other times we use a condition to determine when to stop running the for loop. While the player is alive, we render the video game, and once the number of lives ends, then we finish the game and exit the loop. In this case, We know ahead of time how many times we want to run the loop. Therefore, we will use a for loop. A for loop has the following structure. It contains the word for, followed by what is known as a loop variable. The loop variable is a form of information that represents each of the iterations within the loop. In this case, we're going to call it I. It is followed by the command in. Then we're going to pass the action known as range, and inside of range we're going to specify how many times we want to run this loop. We know the number of times is 4. Everything that is involved inside of the loop has to be indented. This is known as the body, and everything that is indented within the scope of the for loop will be run as part of that for loop. It is to say that the for loop will execute that code for as many times as it is required. Any code that is found outside will not be run until the for loop ends. We want these 2 lines of code, which notice are the basic unit of information in the program, to be the ones that run 4 times. And we get rid of the extra. We just acquire some sort of superpower that allows us to repeat things for as long as we want them to. The pattern also reveals some very important relationship between our data structures, represented with variables, and the structure of the code. What does this number 4 represent? It is an integer, of course, but beyond that, how is this 4 different than this 100? And this 100 different than this 90? What are these numbers for? That is the most important question that we can ask in this code snippet. The code represents the number of sides, whereas the 100 represents the size of each of the lengths of the square. And either by process of analysis or elimination, we can conclude that this represents the angle. If we run the program once more, the result should be the same. Before we keep moving forward, let's talk about something very important for those of you who are new in the programming language of Python and any programming language at all. What are these elements that are followed by brackets? These elements followed by brackets represent actions. In the same way that the English language has sentences that are divided in a subject and a predicate, like the dog barks, where the dog is the subject and barks represents the predicate with only the verb. In Python, barks would be the name of the verb, the action, and the dog is the element that is either being affected by that action or is being the main character involved in such action. Barks, and we pass inside of the brackets the element that barks, which is the dog. This is how we can transform English into code and pseudocode. Now that we have this program representing an emergent level of complexity that appears by the interaction of 4 different sites joining together to form a bigger shape, let's put them inside of a compartment so that we can access them in a way that is practical and only when they get called. This is what a function does. We start by calling def, which stands for define or definition, and we call this the first function. Let's call it make a square. We follow that with open and close brackets, and inside we're going to pass the size that our shape is going to have. This function is an action especially defined to create a square. That's its only job. It can make a square of any size imaginable. How do we call this function? Notice that the use of the colon followed by indentation follows the same nomenclature that we apply for the for loop. Everything that is within the indentation is considered to be part of that for loop. To call a function, we just need to acknowledge it's there, followed by the brackets, just like forward or right. And inside we pass the information that this function requires. as we specified at the moment when we created it. We run the program again and the result is the same. But now we can focus on the process of having a square as the new basic unit of information in the system. Let's draw another square for I in range 4. We move forward and we turn right. Notice that the process of drawing a square uses at its foundation the idea of drawing a line, which represents the basic unit of information. But what if we play naughty here and we take line 33, which is the call to the function make a square, and we paste it in line 35, this time making every single side of the square its own square. Let's run it again. Interesting. We got a compound shape. This, for the program, still has the structure of a square. You can see the for loop there. What happened, however, is that by replacing every side of the square by another square, we increase the complexity. But we don't need to stop there. How could we? Let's repeat the variables we had before, because this is still a square. And let's put it inside of its own function. Let's call this function make a square degree 2. And this also takes the size. We put all of the information inside of the function and then we move forward. Let's draw another square. We take the size, we move forward, and we turn right. Except this time we modified the basic unit of information of this square for the function make squares degree 2, which also takes the size. Oops, this value should be sides. Hard to see with the microphone in front of my face. I apologize for that. And at this point it may be a good idea to speed the process. So the turtle has a command called speed that, if set to 0, increases the speed of the turtle. And okay, now we get an interesting pattern, but at this point it looks exactly as the previous result. Let's modify this value of 90. Instead of the angle, let's divide the angle by 2. And then we run it this time. We get a more interesting shape. Let's divide it by 4. And we start making art. We're almost done. Let's make things more interesting by animating. Notice that the whole concept of our program is summarized in these 3 lines of code. That part hasn't changed. The program has gotten more complex, and we have described that complexity somewhere else, inside of helper functions. Actions whose primary purpose is to assist the programmer by reducing complexity so that we can focus on the big picture. I'm gonna run this 2 times, not 4, and I'm gonna make the angle 45 degrees. This will visually give the same effect that we already had. Now I'm gonna add a new action called begin fill, and I'm gonna wrap it at the end by end fill. This is gonna fill the square with the color black. Now let's start the process of the animation. We start by setting tracer to 0, which is the animation command of the turtles. It says, I don't want to see the turtle drawing every single line anymore. I just want to see the final picture, so draw it as fast as you can. At the end, we need to manually ask to update the images. And before we start, we also need to clear it. All of this code, wrapped inside of the hashtags, has to be inside of an infinite loop. A loop that will run forever. This is opposite to for loops. We not only don't know when to stop, we don't care stopping at all. And if we run the program now, the result will visually be the same. However, the program is still running. Now, let's add a new variable called the offset. This in the data definitions. An offset is gonna be a float, and it represents an offset applied to the initial value of angle of rotation to make a shape. Let's set offset to 0. And the purpose of our program now is going to be to update the value of the offset, but making it equal to itself plus 1. If the offset plus 0.01, something small. Notice that if the offset is 1, we make it equal to 1 plus 0.01. We are not resetting the variable. We are just updating it, making it a little bigger or a little smaller. And we just need to apply the offset somewhere here. Let's start experimenting. Let's put it here first. Rather than rotating 45 degrees, let's make it rotate the offset. And before we start doing anything else, let's make sure that we set the rotation back to 0 at the beginning so that the turtle can show the patterns clearly. Otherwise, if the turtle finishes the previous iteration of the program already skewed, the next iteration on the program will simply add the offset to that previous skew, therefore rendering some weird results. To do this, I'm just gonna call the turtle to go home. If I run the program once more, you can see that something starts happening. Animating stuff and adding colors can really increase your perspective of the complexity of a mechanism. However, we don't really see the big picture, and that is because we are using Windows. Unfortunately, because I love Windows. If we really want to see the main scope of this program, we need to use a Linux-based system. I'm gonna use the Replit editor, an online way to create programs using Python and other programming languages. I'm gonna go to the top left corner and I'm gonna create a new turtle template that I'm gonna call demo. Once the program is created, I'm gonna get a window that looks nearly identical to that of VS Code. I wonder if it is for a reason. Now the program is exactly the same, but if I run it in Replit, let me increase the speed of the animation, you'll notice a clear difference. The reason is because the Windows system understands overlapping areas when trying to fill two shapes with color as just filling those areas with the same color, whereas Linux leaves those areas empty. Intersections in Linux are left blank. So this is the end of our tutorial. I hope you had a good time following along. And to summarize, what we did today was focusing not only on the syntax of the programming language, but rather on the concept of data definitions and algorithms to create shapes. As a demonstration, let's simply modify our system at the top. Instead of a shape with 4 sides, let's change it to 5. If the program is well written, it should automatically modify its behavior. And it does. The more sides we have, the more complex the behavior will be. I'll see you next time.